Now let's move to the flow simulation using a dual media model approach. This approach tries to describe separately the two media, that means the rock matrix and the fractures network. The dual media model approach is at present the most popular one in the oil and gas industry for flow modeling of naturally fractured reservoirs. The approach relies on a kind of abstract idealization and simplification of the real fracture system, where matrix and fractures are treated as separate entities in each cell, using a sugar cube geometry describing the rock matrix blocks as surrounded by the fractures inside each cell. The simulator tracks matrix and fracture pressures and saturation change in each cell, describing the transfer of fluid between the two media. There are different types of dual media model, but the most common utilized in the oil gas industry are the dual porosity single permeability and the dual porosity dual permeability. The former one is characterized by no matrix to matrix flow. That means that the fluid flow between cells is only the prerogative of the fractures and is function of fractures permeability and aperture. In this kind of model, the matrix contributes to the fluid flow just inside the cells, feeding the fractures of the cell, and is function of matrix permeability and matrix fracture contact interface area. In fact, this model is utilized for context where the fractures have a primary role, being their cell-to-cell transmissibility by far larger than that of the rock matrix. Moving to the dual porosity dual permeability model, this model is utilized for context where the rock matrix transmissibility values tend to approach those one of the fractures. The matrix-to-matrix flow between cells is also effective, being function of matrix permeability and matrix-to-matrix interface area. Therefore, in this model also the matrix-to-matrix flow between cells is active. The drawback is that the computational times are about doubled, suggesting to use as much as possible, when suitable, the simple dual porosity single permeability model. The interplay between matrix and fractures inside each cell is controlled by the matrix fracture transmissibility coefficient that is related to three factors: the rock matrix permeability, the cell bulk volume, and the shape factor, sigma, that is related to the geometrical characteristic of the discrete fracture network. In fact, this later parameter describe the shape of the rock matrix blocks in relation to the fracture spacing in the three directions. When the fracture density increases, the fracture spacing decreases and the shape factor increases. As a consequence, the matrix fracture transmissibility coefficient increases. That means that the fluid flow from the rock matrix block to the fractures is increased because there is a short distance between the fluid inside the rock matrix and the surrounding fractures. Considering that fractures are generally quite steep and that horizontal fractures are quite rare and partly closed because of the overburden, the vertical spacing is generally assumed very large, stretching to infinity, so not significantly impacting on the shape factor. We can now try to list the pros and cons of using dual porosity model versus single effective model. The dual porosity models are better in capturing the matrix fracture interaction, the recovery mechanism, and the simulation of the fracture flow channeling in context made by sparse fractures occurrence. However, using a more detailed description of the fracture network, they need more data to describe more variables that are sometimes hard to define. Moreover, dual porosity models have longer simulation run times that sometimes are minimized using coarser grid with the drawback of losing the geological resolution. So a balance or a kind of compromise has to be found. The single effective model is better in context made by dense fractures occurrence that makes the fractured rock more homogeneous, and in single-phase fluid context like gas reservoir not affected by water influx.